Okay? So what we do is we write it as v minus pi r square equals to 0, and that is g. Okay, so that's our constraint. G equals to 0. Therefore, g is v minus pi r square h. Does it make sense to everybody? So now you can see how any equation can be written as g equals to 0. Right? Does it make sense to everybody? Or okay. What is f? F is a function we have to optimize. So what is f?
Surface area.
And that is
2 pi r plus pi r squared. 2 pi r squared.
2 pi r h plus 2 pi r. Right? Great. So now we call this new function, let's say f bar, which is f plus lambda g. Yeah.
Does that work both ways? You want to maximize or minimize?
Yes.
If you want to minimize, do you put a negative?
No, it works exactly the same way. In fact, if you will notice, in this case, I'm not going to prove to you whether it's a maxima or a minima, because to do that, you have to take second derivatives, and I'm actually not going to do that. I'm going to invoke basic thinking to argue that it has to be the minima in this case. Okay, all right. So where was I? So yeah, so f plus lambda g. So f is already 2 pi r h plus 2 pi r squared plus lambda times g, which is v minus pi r squared h. So that's our f bar. Okay?
Why only one?
Sorry?
Why is there only one lambda?
Why is there what?
Only one lambda?
Because there's only one constraint.
Okay.
Okay? Alright, so now we do the standard approach. We say f bar. So let's say del f bar, del, let's say r equals to 0. So that will give you an equation 2 pi h plus 4 pi r plus lambda times what? What's the derivative of that?
Negative 2 pi r.
Very good. Minus 2 pi. Right? Yeah? And of course this has to be equal to 0. Right? Okay? Now we do the del f bar, del h equals to 0. And we do that, you're going to get 2 pi r plus, or I guess minus, pi r squared lambda. Right? Yeah? Okay, so now you can see that actually, now of course with the third equation, what will be the third equation?
df2 lambda.
Equals to 0, what will that give you?
G minus pi r squared h.
Exactly, it will give you basically back your constraint, right? So I'm not even going to write it because we already know what that will give us. Okay, so from these two equations you can see, we can, from this equation, we can solve for lambda in terms of r, and we can plug it back there. So from this equation, you can see lambda is simply 2 pi r divided by pi r squared, so 2 over r. Right? Yeah? Okay, so now of course you can plug this lambda in this equation. When you do that, you get 2 pi h plus 4 pi r minus, so lambda is 2 over r, so RR cancels and you become minus 4 pi h. Right? Yeah? Okay, and therefore you can see you get 4 pi r equals to 2 pi h. Therefore, h equals to 2r. Okay? That gives us a relationship so that for height equals to the diameter. Right? And of course, how are you going to figure out h and r? Plug it back into the constraint. So V, volume, is fixed, is pi r square h. And h we can write it as 2r. Therefore, you get r would be simply V divided by 2 pi to the power 1/3. Right? And h, of course, is twice of that. Okay? Sorry? Yes? Easy peasy? Lemon squeezy? Okay. Yeah?
So h equals 2r is the optimum volume for
No, the volume is fixed.
Okay.
So that represents, now of course you could ask me, well, it represents an optimum, but how do we know it's the maximum area or the minimum area, right? So you can certainly take the second derivative. This is a function, so now, you know, we are optimizing as a function of two unknowns. You can take the second derivatives, you can calculate the determinant, and from there you can figure out what it is, right? But you can also physically sometimes argue what it is. So to do that, if you think about it, you can always, you only got one solution, right? So what this means is that if this is a maximum, and you can always think of unlimited value, you can always think of limiting cases. Like you can always think of r goes to infinity and h goes to infinity as two limiting cases, right? Because you're looking at r and h. Right? So we are looking at r versus r and h. So we are looking for solutions in this space. So we know that clearly this r goes to infinity and h goes to infinity are potential solutions, right? Or extremes. So we have, so now the question is, when h goes to infinity or r goes to infinity, does the area go to infinity or 0? Does the area go to 0?
If r goes to infinity, h goes to infinity? The volume goes
Sorry?
the volume is infinity.
Right, so in fact it's an interesting question. What do you guys think?
Infinity.
As
R goes to 0, h has to go to infinity. You have to maintain the
no, as h. Right, but one goes to infinity, the other goes to 0. So how do you know what happens to the product?
Well, I mean, it never equals 0, but it approaches 0.
But how do you know it doesn't approach infinity? It approaches infinity. How do you know that? Well, you have to just look at you have to rewrite in terms of, right? So we know that s equals to 2 pi r L plus 2 pi r squared. When r goes to infinity, we know this term goes to infinity anyway. So we don't even have to worry about that. Right? So we know that if r goes to infinity, clearly surface area goes to infinity.
You said volume.
Huh?
Did you say? I thought you said volume.
No, volume is fixed. Oh, sorry, did I say volume? No, I meant surface area. Volume is fixed. We can't change volume.
Oh yeah, that's right.
Right? The question is what happens to surface area. And we know as r goes to infinity, surface area goes to infinity, right? So that means the solution we have must be a minimum. It cannot be a maximum because the maximum appears at r goes to infinity. Does it make sense?
I don't see how, I still don't see how you're concluding that it's a minimum.
Well, because if, how should I say this? You know that if you're looking on a complex landscape, if there is only, if at infinity both is a maximum on both sides, the limit has to be minimum. if it's if it's 0 at both sides, the center has to be maximum, right? Because between any two minimum has to be maxima, between any two maxima has to be minimum, right? Does it make sense?
You don't rule out the possibility of additional, like it could have, even if it's bounded by going up to infinity, it could have a minima and two maximum.
Very good, but it can't because we only found one solution,
Right.
right?
That's why you're bounded.
Exactly. Because we found only one solution, therefore we can just look at the infinity, find out what the values are, from there we right away know what the solution is, right? So if as r goes to infinity and h goes to infinity, the solution would have been s actually is 0, then we would have known this is a maximum, right? But of course that's not the case. All right. Now let's do one more example, and then I'll probably let you go early. Okay, so let's do a problem where we have 3 reactors in series. Okay? So let's say A comes in, reacts, this goes here, and this finally comes out. Okay? And the reaction in each case is a first order reaction. So let's say the concentration here is Ca0. What's going to be the concentration here? Does anybody know already? Kinetics.
CA naught 1 minus x.
Okay, 1 minus x, and what is it in Boltzmann? It's the same thing. What is it in terms of rate constant K, let's say? Well, I guess I mean, we should write the equation anyway. So inlet is Ca0 times Q, right?
Oh, it's volumetric flow.
So the flow rate is Q. So inlet must be equal to outlet because we are looking at steady state. What is outlet? Outlet is Q, Ca. Let's call it Ca1. What else? Plus reaction, right?